Up on the board here, we've got the data that's given to us from problem 50 from your textbook. We're given this table of values for t and v of t. T is time measured in days, and it's days from the time that a treatment, an ABT 538 treatment, which is for HIV, was begun. And then v of t is the viral load in the HIV patient in question. And the units there are kind of complicated. They're themselves already a fraction. They're RNA copies per milliliter. Okay, now we're given this table of values. One thing I want to point out is whoever collected this data did a bad job. Can you see why? The reason is that the time intervals are not evenly spaced. In general, it's a good idea to take measurements at evenly spaced intervals. Now, we're given this data. There's nothing we can do about it. It looks like we started out measuring things every 4 days. So it would be nice if the next time was 12 days and then 16. But for some reason, whoever gathered this data gathered things after 3 days here, and then went back to 4 days, and then jumped to 7. So that the data wasn't taken at regular time intervals. Now, there's nothing we can do about that. We don't have access to this patient to be able to go back in time and take new, more accurate measurements. But if you're ever the one setting up an experiment or setting up an observation, something to keep in mind is that it's preferable to have evenly spaced measurements. All right, now I've graphed the information over here. So time is on this axis and viral load is on this axis. And you'll notice I'm using a different scale on the two axes because with time I only needed to go up to 22, but with viral load I needed to be able to go all the way up to 53. Okay. Now just looking at this, either from the table, but I think easier to spot in the graph, I can see that as time is passing, the viral load is decreasing. More than that, I can see that it's not just decreasing at a constant rate. It looks like it dropped very suddenly initially, and then it continued to drop, but at a slower rate. Okay, so that's kind of interesting. What I want to do now is use this data to actually calculate a couple of rates of change and estimate an instantaneous rate of change. Let's suppose that the time we really care about is this time 11. Okay. What I'm going to do is I'm going to calculate the average rate of change over the time interval, including this time and the time before it. So the average rate of change over the time interval 8, 11. Now, I know that an average rate of change is just the slope of a secant line. So I'm basically drawing in the secant line. Whoops, that's the wrong secant line. Sorry, I'm drawing in the secant line connecting these 2 points. And I'm just going to call this M1 because we're going to be calculating several slopes. Okay. That's going to be the rate of change over that time interval from 8 to 11. And we want to make sure that we take a look at what the units are as well. Okay, so this is just going to be M1, which is just rise over run. So that's going to be the change in Y, 9.4 minus 18, over the change in T, 11 minus 8. So let's see, that's going to be a 3 on the bottom, and that's going to be a negative 8.6 on the top. Now, I never want to leave an answer like this where I'm mixing fractions and decimals. Either make it a fraction or a decimal. In this case, I don't want to convert to a decimal because I can see it's going to be an infinitely repeating one. 3 doesn't divide evenly into 8.6. So what I'm going to do is just multiply by 1 in the form of 10 tenths. That makes this negative 86 over 30. Okay, now I can reduce that a little bit because 2 goes into both of those. So that's going to be negative 43 fifteenths. Okay. Now, what are the units for that? Because that's a rate of change. Now, I got this as just rise over run. The rise was the change in the viral load. So that was RNA copies per milliliter. And then the run was time in days. So I can think of the units as this complex fraction, RNA copies per milliliter per day. Okay. So basically we're saying this went down 43/15 RNA copies per milliliter every day, on average, over the days between day 8 and day 11. Now, I could also rewrite this as RNA copies per milliliter day. Just like with plain old regular fractions with numbers, dividing by days is the same as multiplying by 1 over days, and so that puts it into the denominator. So very often you'll see units that look something like this. Generally they come from some sort of a complex fraction. They're basically a fraction of change in this over change in that, but one of those things might have itself already been a fraction. Okay, excellent. So we've got that. So I'm just going to write that in here as M1 was negative 43/15. Okay. Now, let's calculate the average change in the time interval that we have after time 11. Okay. So that would be going from 11 to 15. So again, that's going to be a slope of a secant line. That's just going to be this secant line, which will have slope M2. Now, the line isn't the same as the slope, but I'm just drawing the arrow to say M2 is the slope of that line. Okay. So M2 would just be rise over run. The rise would be the change in the viral load. So that's going to be 5.2 minus 9.4 over 15 minus 11. So again, that's going to be negative. This is a good thing. We want this treatment to be working, so we want the viral load to be dropping. Okay. That's going to be negative 4.2 over 4. Again, I don't like mixing those fractions and decimals. Multiplying by 10 over 10, that's going to move that decimal, so negative 42 over 40, which will reduce to negative 21 over 20. And again, that's going to be in RNA copies per milliliter per day. And whether you want to write that as a complex fraction or as just a more simple fraction, but with the denominator as milliliter days, is up to you. Either is perfectly acceptable. Okay, now those are the average rates of change, and those we can get exactly because they're just slopes of secant lines, and we've got the values at the endpoints. Now, if I wanted to, I'm going to just make a note here that M2 was negative 21 over 20. If I wanted to estimate an instantaneous rate of change, I can only estimate that. But let's say I wanted to estimate V prime at 11. That would be the instantaneous rate of change in the viral load at day 11. Okay, now I can't calculate that exactly because that's going to be the slope of the tangent line, and I don't have the entire curve. I just have these 5 points that are on it. But I could estimate it. And again, there are two basic ways that I could do that. One is I could draw in the simplest curve that I can, connecting the dots, and then try to estimate the tangent line, actually draw it in, and then measure its slope. That would be a lot easier to do if I felt like I had a very accurate graph, and I feel like I don't. So what I'm going to do instead is I'm just going to average these two slopes, the slope of the secant line I got using the closest point to the left, and the slope of the secant line I got using the closest point to the right. So that would be negative 43/15 plus negative 21/20 divided by 2. That's the average of those two average rates of change. Now, one thing that I might choose to do, because this was a lousy data set and the point to the left was only 3 days away, but the point to the right was 4 days away, this point was closer. So I might, if I really wanted to, calculate a weighted average where I gave more weight to this slope. I'm not actually going to do that. I'm just going to take the plain old regular average here. But I just want to point out different strategies that we can have. But I wouldn't have to compensate for a lousy data set if my time intervals had been evenly spaced to begin with. So when you're doing research and you're setting up an experiment or you're setting up an observation, super important that you try to set it up correctly, because whoever's working with your data is stuck with what you give them. Okay, so let's see. Looks like I'm going to want a common denominator here. So I'm going to multiply this by 1 in the form of 4/4 and this by 1 in the form of 3/3 to get a common denominator of 60. So we're going to have negative 172/60 plus a negative 63/60, all divided by 2. So that's going to be negative 235/60 divided by 2 is times 1/2. And I can do a little bit of reducing because 5 goes into the top and the bottom here. So 5's going to go in here 47 times. 5's going to go in here 15 times. So that's going to become negative 47/30. And the units would be the same as the units for the slope of a secant line, because it's still rise over run, even though I wasn't able to calculate it that way because I didn't know 2 points on the tangent line. But this would just be RNA copies per milliliter per day. Okay, before I end the videos for this section, I want to just comment briefly on a couple of homework questions. 37, 39, and 41. Now, 2 of these, 37 and 41, I don't actually assign until we've covered the next section. That's because we've been looking here at the slope of the tangent line, the derivative, as being the limit of the slope of the secant lines, and I gave you one formula for that. We're going to see another version of that formula in the next section. All of these problems give you a limit and say this limit represents a derivative. It represents the slope of a tangent line to a function at a point. Find the function and find the point. I am purposely not lecturing on that in these lecture videos. I didn't just forget. I'm leaving that as a challenge for you in the homework. So, some of you may find that you're totally comfortable with those problems. Some of you may have questions. That's fine. But don't say, oh, she didn't mention this in class. It must not be important. I'm purposely not lecturing on it to leave it for you as a puzzle to try to figure out. If you have questions, I'm more than happy to work on that puzzle with you in office hours.